Hello, my friends, and welcome to this explainer. I'm absolutely super excited to have all of our YouTube subscribers here with us today because today we're taking a really fascinating journey under the hood of modern AI. You know, everyone's talking about these massive large language models, but honestly, very few people actually understand what's happening at the pure mathematical level. So today, we're going to completely demystify transformer math. No magic, just pure, beautiful step-by-step logic. Let's get started, shall we?
Okay, let's dive right into this. Have you ever wondered how a machine, something that literally only understands ones and zeros, can suddenly write poetry or debug your Python code flawlessly? I mean, it doesn't have a brain. It relies entirely on a highly structured sequence of math. So, over the next few minutes, we'll follow the exact, step-by-step journey of a single word and see exactly how it gets transformed.
And hey, please don't worry if the formulas look a bit intimidating at first. We're going to break this all down into 5 very logical steps. First, words to numbers. Second, the attention engine. Third, multiple views. Fourth, stability. And finally, the feed-forward step. Simple, right? Let's take it one step at a time.
All right, step 1, from words to numbers. This is exactly where our journey begins.
Simply put, computers can't just take the word bank and feed it into an equation. They only deal with continuous vectors. So, take a look at this fundamental formula. X equals the embedding of X plus PE. First, we convert our word into a meaning vector. But here is the major catch. Transformers process every single word in a sentence at the exact same time. They have absolutely zero built-in sense of sequence. So we add PE, positional encoding. This cleverly uses sine and cosine functions to stamp a unique mathematical position tag onto the word. Let's look at a concrete example to make this crystal clear. Say our word is bank. Its embedding vector gives us the raw dictionary meaning. Let's just say it's an array of numbers, like 0.2, 0.8, and so on. Then we calculate its positional encoding based on where exactly it sits in the sentence. We literally just add these two arrays together, and boom, we get our final input X. Now the word bank has its own unique numerical identity.
Moving right along to step 2, the engine, the famous attention mechanism. Now we are entering the absolute core of the architecture. Behold, the scaled dot product attention formula. I know it looks a bit heavy, but it is actually brilliant. We multiply our input by learned weight matrices to create 3 brand new vectors for every single word: queries, or Q, keys, or K, and values, or V. We take the dot product of Q and K transposed to calculate a raw similarity score between every single word. Then we scale it down, apply a Softmax function to turn those into percentages, and finally multiply by V. And this brilliantly illustrates exactly how Q, K, and V function together in the real world. Think of it exactly like searching a database. The query is asking the system, hey, what am I looking for? The key is responding, here is what I have, and the value is the actual content. So if our word is bank, its query might be out looking for context. It compares its query to the key of the word river. Because those concepts are highly related, the dot product score shoots up. That means bank is going to pay a massive amount of attention to the value of river. Now, here is a very crucial question. It's actually a favorite in tech interviews. Why must we divide that dot product by the square root of d sub k? Why do we desperately need this scaling factor? Well, my friends, the math completely demands it. If we just use a standard dot product without scaling it down, when we're dealing with high dimensions, like 512, that multiplication makes the values grow excessively large. And when you feed massive numbers into a softmax function, it aggressively pushes all the probabilities to absolute ones and zeros. The gradients become tiny. We call this the vanishing gradient problem. It's literally like a car engine just stalling out. The model simply stops learning. By dividing by the square root of dk, the scale dot product keeps those numbers small and manageable. It pushes the softmax right back into stable learning regions. It's a mathematically elegant fix. Next up is step 3, multiple views, also known as multi-head attention.
You see, looking at a complex sentence from just one single perspective is simply not enough. And this brings us to the multi-head attention formula. Instead of doing one massive attention pass, the architecture splits those Q, K, and V matrices into smaller chunks, which we call heads. It calculates them completely independently, all in parallel. Then it concatenates them back together and multiplies by a final weight matrix, WO, to restore the original dimension. But why do we do this? Because human language is deeply multi-layered. Look at this example here.
Head 1 might be focusing strictly on the grammar, trying to figure out who did the action to whom. But at the exact same time, Head 2 is focusing on context. It's trying to figure out if our word bank is sitting next to a river or if it's a financial building where you deposit your cash. Splitting into multiple heads allows the model to attend to all these different representation subspaces at the exact same time. All right, moving to step 4, stability. This covers residuals and layer norm. Training these deep AI models is a chaotic, mathematically intense process, so we desperately need stability. First step, we use residual connections. Without them, in really deep networks, the learning signals, the gradients, often just die out before reaching the earlier layers. So we do something remarkably simple. We take the original input x and literally just add it to the output of the attention layer. It acts exactly like a bypass lane on a busy highway, ensuring those gradients can flow backward easily and keep the learning alive. And right after that addition, we apply layer normalization. This formula is absolutely key for keeping data stable during training. It calculates the mean, represented by mu, and the variance, represented by sigma squared. We also add a very tiny constant, epsilon, just so we don't accidentally divide by 0. Finally, we multiply by gamma and add beta. Now these are actually parameters the network learns, so it can perfectly scale and shift the data for the next layer.
So the crucial point is how this actually maps to reality. Think of a classroom where one exam was out of 100 marks and another was out of 1,000 marks. You can't easily compare those scores, right? Layer normalization does exactly what a smart teacher does when they normalize test scores to a standard curve. By mathematically adjusting the mean and the variance, it ensures that no matter how crazy the numbers get inside the network, they are always securely reset to a stable, comparable baseline before moving on.
Finally, step 5, feed forward and final prediction. My friends, we are in the final stretch now. The vector passes into the feed forward network. The formula here consists of 2 linear transformations separated by a nonlinear activation function. We take our input x, multiply it by weight matrix W1, and add a bias, B1. Then, the ReLU activation function simply looks at the data and throws away any negative numbers, replacing them with 0. After that, we multiply by W2.
To give you a concrete example of how this dimensional projection works, in step 1, W1 projects the 512-dimension data all the way up into a much higher dimensional space, typically around 2048 dimensions. It expands the data massively so it can find really complex patterns. In step 2, ReLU aggressively discards those negative values, which adds crucial nonlinearity to the model. And in step 3, W2 projects it right back down to 512 dimensions. Honestly, it's a lot like unpacking a heavily compressed file, analyzing everything inside, and then neatly packing it back up again.
And now, that abstract math has to convert back into our human vocabulary. The outputs from the top layer are passed through a final linear layer. This maps our 512 dimensions into a massive vector that is the exact size of our dictionary. This gives us raw scores, which we call logits. Then, a final Softmax layer steps in and normalizes these raw scores into very precise percentages. What's really fascinating here is how the math boldly declares a clear winner. Out of tens of thousands of words in the entire English dictionary, the Softmax function gives us actual probabilities. For the context of bank, maybe the word river gets an 85% probability, account gets 10%, and the gets just 5%.
And exactly as the architecture dictates, the index with the highest probability value is chosen as the next predicted word in the sequence. Our model mathematically observed the whole sentence. It weighed the importance of every single word using those attention matrices. It stabilized the signals, projected them through the feed-forward networks, and then confidently printed out the word river. The journey of that single word is complete. We literally went from English words to pure vectors through an incredible engine of attention and right back to a human word again. It is incredibly elegant engineering, but it leaves me with one final thought for all of you. If these exact mathematical foundations, just matrices, dot products, and scaling factors, can completely master the subtle nuances of our language today, what human barriers will they decode tomorrow? Thank you so much for joining me on this explainer, my friends. Keep learning, keep building, and I will see you